In this video, we're going to focus on the electromagnetic force. So looking at a force field where all the magnetic force is coming from electricity, and we are experiencing a force either on a current carrying wire or some charged particle that's moving through a magnetic field. So let's look at the right-hand rule that we started with in the last lesson. You might remember this idea that if you grab onto the wire with your thumb pointing in the direction of the current, your fingers will wrap around the wire in the direction of the magnetic field. So whether you're looking here up at this top one, thumb goes to the right, your fingers wrap from the top to the bottom, or out of the screen on the top and into the screen on the bottom. Or you're looking at this bottom one where your thumb points to the left, where your fingers are wrapping from the bottom to the top or out of the screen on the bottom and into the screen at the top. We can draw in and depict what that magnetic field is going to look like around this wire with a current through it. Now, in this case, we're not looking at force at all. All we are looking at is how a magnetic field forms around this wire if it has a current running through it. So now let's look at what happens if we start to factor this in with an already existing magnetic field. We'll see a force start to take place. To do this, we need to look at right-hand rule number 2. Well, you might remember here this idea of into the paper, out of the paper, into the screen, out of the screen, represented with an X and a dot, respectively. Well, right-hand rule number 2, we are going to use our right hand as kind of an open palm right hand, and the thumb is going to point in the direction of the current. Your fingers will point in the direction of the magnetic field lines, and your palm points in the direction of the force. An easy way to remember this is if you had an open palm, your palm would just push in that direction. So thumb in the direction of the current, fingers in the direction of the field lines. Those will always be 90 degrees from each other, and your palm will point in the direction of the force. In this case, I'm drawing it as an out of the screen dot. I think it's easier to see this in action and to make it not as confusing with the video and not necessarily knowing which hand it looks like when I am gesturing. I have taken some pictures of my hand representing different directions. You're going to want to use your right hand to actually figure this out. So let's imagine we have a current carrying wire placed in a magnetic field, and the magnetic field exerts a force on the wire. Well, we're going to use right hand rule number 2. Remember, thumb in the direction of the current, fingers in the field, and palm with the force. So here we know that our magnetic field, as we talked about in the last lesson, will always go from north to south. So here I have a horseshoe magnet where the field lines go from north to south. And currently I have a wire with a current going into that magnetic field. And it's kind of drawn at an angle here, but you can imagine essentially that is going straight into the board or into the screen. So the way I'm going to represent that is my fingers are going to go point from north to south, and my thumb is going to point in into the screen, showing that this is going into the magnet from the front to the back. And in doing so, my palm is pointing up, which means that this wire is going to experience an upward force on that wire. Here on this other side, I still have north to south, but now you'll notice that the wire is going out. It's coming from the back to the front. So if I were to position my hand accordingly, my fingers still have to go from north to south, and my thumb has to point from the back to the front. So basically out of the screen. So I'm facing it here if I'm looking at this, where my thumb is pointing out at me. And that causes my hand to point down or push down, which means this is going to experience a downward force. I would highly recommend to try to orient your hand, like actually try this to see if you can recreate these same sorts of situations. Well, looking at a little bit more complicated setup, we might have a situation where you have a wire that the current is coming in, and then that wire loops. It might coil once, it might coil 100 times, but when it coils around, one side is going in from the front to the back, and then the current comes out from the back to the front. And here it's flowing through that magnet. The magnet again is north to south. So now what happens is on the left-hand side here, where the current is going in, we have the field lines going from north to south, but my thumb is pointing into the screen, which creates an upward force. And on the other side, My thumb is pointing out, but my fingers are still going north to south, which is producing a downward force. And it's kind of hard to see the three dimensions here in a picture. It's about as good as it can get. But what you're going to notice here is if you have this set up kind of at an axle, you're going to cause this to start spinning. You're going to get some motion here. This is a very, very basic diagram of a motor that you have this magnetic force causing an upward here, downward here, and when you push it like that, you're going to see this spin. You're going to need to do some tricky things to switch the current so they can continue spinning, but that is a very, very simple design of a motor. So that brings us to a couple words that you've probably heard of before, motors and generators. Well, a motor, just like this last example, it converts electricity into motion. So we are able to run electricity through a wire and have that wire in a magnetic field. When the electricity runs through the wire, it responds with the magnetic field, creating this motion, moving it up or down, or like we saw in that motor, around and around. If you take that same setup and you actually move the wire in the magnetic field, you can create current flowing through the wires. So electric generator can take motion and convert it into electricity. So here are a couple examples of this. You might see this setup here where you've got a loop running in this magnetic field and set it up with a battery. When that battery is hooked up, you'll see that the current will flow through. When the current flows through in that magnetic field, you will start to see this motion. You'll notice here this brushes and commutator. This is basically just there to set up so that the current switches when it gets to a far enough place so it doesn't spin to the point that it just stops. It'll switch and then can continue moving around. Here's another example showing just the opposite, where you have a mechanical input rotating a loop, and that results in some sort of electrical input or electrical output. Another function of this, or example that you might be able to use with this, is speakers. A speaker is basically just using a current flowing through a wire and switching that current really rapidly to match the frequency of the sound that it's trying to produce. And whenever it switches, it changes the direction of the force. And it creates that force because there is a magnetic field surrounding that speaker coil. So here's a good example. Let's say we are just going to cross section one part of this coil. It's kind of wrapped around this magnetic structure. And we look at one side where all of the um, current is coming out because that's the way that the current is designed to run. In this case, in north to south, we know that we have a direction of the field lines going from the north to the south, and my thumb has to point out because the current is flowing out. I'm going to produce a field going downward, but all I have to do to switch the field is to switch the current. So if I switch the current and now the current is going in, I still have a field going from north to south. My fingers point in that direction, and my thumb points inward, creating this upward force. And if I switch that fast enough, I can create this force causing a vibration to happen. And all a speaker is doing is vibrating at the right frequency to produce the sound wave that you are trying to create. This same concept is actually where the definition of the ampere comes from. IB every once in a while will like to ask about this, as it's a little bit more advanced of a situation to try to picture. So I'm going to do my best to diagram it out here. Consider two parallel wires with a current in the same direction. Let's imagine, like, are they going to attract or will they repel? Well, here we have it drawn that they're on the screen in front of us. Here is that same setup as if we were looking from the top down. So notice here, I've drawn in that current as just simple dots, showing that the current is coming at us because we are looking at this diagram from the top. Well, if I use my right hand rule, I can draw in what the magnetic field looks like around this wire here on the left. The right hand rule with my thumb coming out at me shows that the magnetic field will go around counterclockwise here. Well, if I extend that out and I keep going, I'll notice that as I extend that magnetic field outward, that this other wire is in the magnetic field, and that magnetic field at that location is pointing upward. Well, now I can use my second right hand rule and notice that I know the direction of the magnetic field. and I know the direction of the current going through that wire. So using my right hand as a flat right hand rule, thumb pointing outward at me, and my fingers going in the direction of the magnetic field, which is upward here, based on this diagram, that will experience a force inward. Now, if I do the same thing looking at the other wire, so imagine that I'm drawing the magnetic field around this wire on the right. I still have a magnetic field where the thumb is pointing out at me and my fingers wrap around counterclockwise. And if I extend that outward here, I'll notice that this other wire, the one on the left, is experiencing a downward magnetic field. So if my thumb is pointing out, my fingers are pointing down, I will experience this inward magnetic force. So similar to what I saw here, I'm going to see these actually start to pull in on each other, that each wire, the current is producing a force on the other wire, attracting it inward. So if you create this parallel wire setup where each one has a current, they are going to be pulled inward. And 1 ampere is actually defined based on this force. It's defined as the current that would cause a force of 2 times 10 to the negative 7th newtons per meter between two long parallel conductors separated by 1 meter in a vacuum. So there's a lot going on in there, but just so you know what the setup is for that definition, that is an important experimental design to create a situation where each wire experiences this inward force. All right, so we've talked about fields and field strength already. Gravitational field strength is force per kilogram. Electric field strength is force per coulomb or force per charge. Magnetic field strength, this capital B, the B field, is force per current. So we'll see newtons per amp, and that will give us this T, standing for Tesla. All right, this is sometimes called the magnetic flux, and the magnetic field strength here is really dependent on this idea of perpendicular, or be on how perpendicular the current is to that magnetic field. And we'll see that set up here in our right hand rule as well. It has to do with the fact, like, if I have my right hand out, my thumb, the direction of the current, is perpendicular to the direction of the field in that perfect setup. We'll see it's not always the case. But if they are parallel to each other, there will be no magnetic force at all. There will be no, sometimes we call magnetic flux. So the actual equation for this is shown here. The force of the wire is proportional to the charge moving perpendicular to the field. So notice here, if I have a field shown by these blue vectors and a current here shown by this red line, the current isn't perpendicular. But I can figure out based on the angle that it is to this magnetic field, and the length of the wire that's in that magnetic field, I can actually produce and figure out how much of that current is going down, how much of a length of that wire is perpendicular um, to that field itself using this sign. So the sign of the angle is helping us get this perpendicular component of that. You'll see force, and then I times L sine theta. It's just turning current into the perpendicular component of that current. If I rearrange this formula and solve it for force, I will get something that looks like this. F is equal to B times I times L times the sine of theta. It's important that you can recognize what each of these stands for. F is magnetic force, that's in newtons. B is the field strength in Tesla. I is the current still, that's what we looked at before. L is the length of the conductor in the uniform magnetic field, and then theta is the angle between the field and the current. Let's look at an example of this. After we find this in our equation booklet here, we can see in subtopic 5.4, there's this equation here. F is equal to B times I times L times the sine of theta. All right, we have a current of 3.8 amps in a long wire experiencing a force of 5.7 times 10 to the negative third newtons when it flows through a magnetic field of strength 25 millitesla. If the length of the wire in the field is 10 centimeters, what is the angle between the field and the current? So I'm looking for angle. I'm trying to solve for this theta here. The rest is just a matter of plugging in the right number in the right unit. So I know that the force that's provided here is already in newtons, 5.7 times 10 to the negative third. B, the magnetic field is given to me in millitesla. I want to convert that to Tesla. Millitesla is the same thing as like millimeters. You're going to move the decimal 3 places to the left or multiply by a negative 10 to the negative 3. So I've got 25 times 10 to the negative third Tesla. Then I have I is 3.8 amps. And L, the length converted into meters, 10 centimeters turns into 0.1 meters. All right, then solving this for theta, I have to take the inverse sine to get theta all by itself. So it's the inverse sine of F over BIL. Plugging in the numbers that I've listed below, I will find theta to be something that makes sense, like 36.87 degrees. All right, we won't always see this as a force on a wire. Instead, sometimes we'll see this on an actual particle. Particle has charge, and if the particle is moving, then technically there's a current. There's a flow of charge. When there is this magnetic force on the wire, it's really looking at those charges inside. So another way that we can look at this is looking at it in terms of the charge, the actual particle carrying that. Well, to get there, let's just talk a little bit about how the moving charge is related to current. First, let's imagine we have the charge and it's moving. Its velocity is how far it moves, the length that it goes, divided by the time. Well, then we know that the length is just velocity times time, how fast it's moving times how long it's moving for. And we know that current is just coulombs per second, or the charge that moves through per unit of time. So if I substitute some of this stuff in here, well, I know that the current is just Q over T, and the length is how far the charge moves in that amount of time. That's V times T. Well, the time cancels out, and what I'm left with is the magnetic field strength, B, times the charge, times the velocity, times the sine of theta. That's still the angle with the magnetic field that this thing produces. I can find this equation in my data booklet as well. That's subtopic 5.4. All right, let's look at another example that uses this equation. What is the magnetic force acting on a proton? Here's the charge of a proton. It's just the elementary charge, only positive, moving in an angle of 32 degrees across a magnetic field of 5.3 times 10 to the negative third Tesla at a speed of 3.4 times 10 to the fifth meters per second. Well, the charge here in this equation, Q, is 1.6 times 10 to the negative 19th. The velocity is provided as well, already in meters per second. The magnetic field is already in Tesla. And then all that's left for us uh, on this right-hand side is the angle, 32 degrees. All right, when I plug all of that in, making sure that I am in degree mode, I will find that the force is 1.5 times 10 to the negative 16th newtons. That seems tiny, but remember that this is the charge, or this is the force on one singular proton. So that's a really tiny force, but it's a really tiny particle without very much mass. So even though it doesn't have very much mass, it will accelerate, have some sort of acceleration because of this force. Now, that acceleration could be an acceleration speeding up or slowing it down, but most likely here, we are going to see an acceleration that causes it to turn because this force is always perpendicular to the magnetic field or perpendicular to the motion as it's flowing through that field. So let's look at what it does to its actual direction of travel. Let's imagine here that we are moving perfectly perpendicular to the field. So here we've got a proton, and a proton is moving through this magnetic field being shown out of the screen. Well, same rules hold true that my thumb goes in the direction of the current, my fingers go in the direction of the field, and then my palm will push in the direction of the magnetic force. Well, if I set up my hand here where my thumb is in the direction of the current, current, remember, is the direction of the positive charge, thanks to Ben Franklin. My fingers point out of the screen. My force is going to be pushing downward. And it's already moving to the right, so the force is just going to cause it to kind of deflect, change its direction a little bit. If it's moving really, really fast, I can change my direction a little, but it's still going to go fairly straight. If it's not moving as fast, my force will cause it to bend more. And it is possible to actually have this create a circle to get this to accelerate in circles and kind of like look like an orbit in that case. Here, if my magnetic field is out of the screen, my hand is going to be oriented like this, where my thumb points in the direction of the current, in the direction of that positive flow, and my fingers point in the direction of the field into the screen, which means it's push up. Now, the trick here is noting that your thumb is pointing in the direction of that positive charge, but it isn't always a positive charge that's moving. You could have a positively charged particle moving through, rare that you would have a single proton, but you could have that positive charge, or you could have a negative charge moving. But if a positive charge is defined as the direction of our current, we know that a negative charge has to be exactly opposite of that. So if I'm going to use my right hand, I'm going to point in the opposite direction of the direction that the electron is going. My fingers are still going to point in the magnetic field. So here you can see my fingers are pointing out of the screen. My thumb points backwards from where the electron is actually moving to create this upward force. Likewise here, my thumb points in the opposite direction of that electron. My fingers go into the screen because my magnetic field is into the screen and it pushes it down. So whether you do it this way or you keep your thumb in the same direction and then you just imagine that the answer is opposite of what it was for a proton, you should be able to predict the direction of that charge flowing. So as a recap, you should be able to use the right hand rule to both describe how a particle is going to flow and experience a force, or describe how a wire in a magnetic field is going to experience a force. And then you should be able to use these two equations here represented in subtopic 5.4 to calculate the force or one of these other variables based on this electromagnetic force.